Oh, and again, we're just going to look at a possible test question for your upcoming exam. So obviously, the question that I have on screen is on equilibrium that we are going to discuss today. So the question I have is like, let me just read it. A frame is restrained at a joint A and C, as shown in this figure. This is figure 2 that they're referring to. Member A, B, and member BC are pin connected. Yeah, just show you here that this is the pin. Okay, and what else they said? They also told you that a rectangular distributed lateral load. A triangular. Just read what I wanted to hear. The triangular. Okay, so let me highlight that distributed lateral load with a peak of this much at on AB. Okay, a concentrated moment is applied at C, at joint C. Find the supporters A and B. Okay, the first thing that I think we need to look at is that here we are given that there is a distributed load. What do we know about loads? Let me say I had a beam like this one. Like let me say just a bench in a park. So let me say people are sitting on it. People are sitting, a lot of them. So we can just take the average of these forces, or let me not say forces, weight exactly, and show them as just one vector, one weight in the center of the area that they touched. You see? So as in this case, it's not exactly a case like this one, but they are relating because this one uh, this one is like as they said it's triangular. So to find you know that if it's triangular, that means it doesn't act exactly in the center as I said here. It's at slightly above the center of which just from here to here we'll just call it 2 over 3, and here then it will be 1 over 3. That is your center of gravity of the triangle that we have here. So to find the exact force that we're getting at exactly here, it's going to be half base times height. You know that. Okay, so that is going to be our force. Then half is going to be half, and base any number, it really doesn't matter here. It's going to be 30 times height. The height, you take the height of the whole column, the beam, or oh yeah, column is better, and then 3.7. So then you work this in your calculator, and if you did your computation very well, this is just going to be your force. So we can just say this force is just here, and it's a force of 24.05 newtons instead of this one. So we no longer have this one. Let me just erase it. So now I've cleared everything that we don't need. We only have one force here, just concentrated on one point, of which is just like 2 over 3 uh, above. We could just remove this 2 over 3 and get the exact height, right? Choose that. We'll just do that later. Just 2 over 3 of this height, and we'll get this height, and we'll just simplify our stuff. So the next thing, because this thing is not moving from mm, um we should know by now that sum of all forces in the y direction should equal to 0. Also, the sum of all forces in the x direction is equal to 0 again. So we're just going to use one of these things, and also it's not even uh, changing it like sort of bending. You can just say Tokyo, the Tokyo they call it, and moments, sum of all moments should equals to 0 again. So if we're working with equilibrium problems, these are just one of your most important tools. Going to use summation of the forces in x direction and summation of the forces in y and some moments. Okay, So yeah, the other thing just before I just speak too much, another thing that I need to talk about is the reaction forces, of which are our focus point today. So I want us just to focus on this point C. Point C, it's a roller here, it has wheels. So remember Newton there. When an object X is a force on object B, object B is a force on object A, the force of same magnitude, different direction. So if you're pushing this way, there is no reaction because they are wheels, or should I say roller. Okay, consider it like, yeah, it's like wheels. If you're pushing this way, there is no response. But a roller, it's on the surface. Obviously, you were told that it should have a response called normal. So there is a response force or reaction force like this here. Let's look at another. And here, um, obviously we're going to have a response on the y, of which we call that y-x, and we're going to have a response on the axis, and we're just going to call that ax. So the other thing here, this thing is fixed here. It's like we see a straight line that are like planted uh, on the surface. So exactly, we could say also there is a reaction, moment reaction. Let me call it moment A, because if I'm trying to push this thing like exerted force here, it's just going to resist uh, rotating, and it make this reaction again. Okay, back to our huge view. We're here now. Sum of all forces on the y. Okay, sum of all forces in the y. Let's look at of all forces that are like this. So here I think we have cy, or let me just choose a direction first. This way up is positive. What else? Also this way is positive, and this way on the momentum clockwise is positive. These are my directions. Okay, so cy is up, obviously it's negative. Cy. What else is on the y? We have here we had ay. What else we had? Okay, then all the forces that we have now, we can say they're equals to 0. That all only tell us now that y is equals to cy, but we don't know either of these, so just keep it like this. Let's just save it here. Maybe we'll need it in future. Let's come look at the forces along the x-axis. So it's still the very same principle, just looking at all the forces along uh, the x-axis. So what are these forces? This way is positive. I think we have ax here. Here we have what? We have another one here. The force that we just let me just force apply. Let me just call it force apply, or the load. Let me just call it the load is even better. Let me just call it the load. It's also along the x-axis. What else do we have here? Here we have this response. Here we have the load. Here we have nothing. So that also is equals to 0 again. Here, just because we have like two videos here on this formula, we have two videos, just this one, and we know this one. We know this one to be this one. I call it the load. It was 24 05. I just transpose it to the other side. It's just equals to ax. So we just done a very important thing. We have one. We've just computed one value. Okay, let's look at the main event that I'm pointing at right now. So we are just going to take our moments around along the point B, taking our moments around here. So we're going to look at a moment caused by this force, reaction force, that is pointing upward. Um, okay, so remember a moment, or a take whatever you call it, or your professor call it, at an arm. Let me just call it x, and the force. The distance or should be perpendicular to the, or the force should be perpendicular. So these, they need to be perpendicular to each other. If they are not, you need to use a component that is perpendicular instead. So so when we're looking at the moment caused by force cy specifically, it's going to be moment, let me just say, moment by cy, of which is positive clockwise. There is any force here? Oh, there is moment that we're given here. It's also this one is anti-clockwise. It's going this way. This C pushes this thing this way, making it to go anti-clockwise. This one's supposed to be negative, and the moment that we're given as joint C, this one just goes the other way. So let me just put it here: 680. That should equal to 0 again. From here, we could just transpose moment by C, and here we'll be left with 860. Moment by C. Remember, moment by C should be a force Cy, and the arm. We know the arm here. The arm is what? Is 2.75 perpendicular distance. Okay, then from here we can get our Cy by dividing both sides, and you will do your computation very well. And if you did very well, you should get something like 247.27. It's force in newtons, right? Don't forget to give that units. Also here we're supposed to give units. So now we have cy here. We just got, but we did say something here about cy that is equals to a ax, if I remember very well. You could just equate this, both of them, to 247.27 newtons. Okay, cy was if equating this, remember that cy is up, check the positive, and ay, where is ay? Here, I also call it up, so I said it's going up, so yeah, it's going up, then they are both in the same direction. Now we're just going to look at let me just clear the drawing. It's too dirty. Oh, even this show up if I clear it. Okay, so let me just clear everything. I should have not cleared the directions, but you will remember them. I trust you. You'll just remind me if I forgot about them. Okay, so I think we had this and this positive. We also had clockwise as positive. So I'm going to treat A, B as just in separated or if let me say a free member, this one. So, and also look at uh, some of moments about B, looking at considering AB as a single member, is going to equal to, there is a moment that this thing is here, it's attached, or should I say they dig and put it in. So whenever I'm trying to apply a force, it resist it resist the it resist rotating, of which you call that a reaction, moment reaction. So that is going to be a moment by or should I say moment at A. Okay, so what else we have? There are moments around this one. We will have this one that we just calculated, and we pointed it just here. It was, and if you remember that here we had a reaction force of which we called AX. Let me just reaction force AX that we had, AX that we already have a value that was reacting to this. Here it was going this way. So it also caused moment. Okay, it's called a clockwise moment, right? It should be positive moment again. It's moment by AX, and also this one caused a moment. It's this way. It's anti-clockwise. It's negative. Which I call the load, moment by load, negative moment by load. Then I'm just going to work here. Some of obviously some of the moments is 0, should have started there, just came up here, and then moment at A plus moment AX. Remember here, we know the value for AX, of which is the value for X is going, I just have it here. AX is this, which AX, I said it's this way. Oh yeah, it's this way. So it's called a clockwise moment, of which is positive, so it's going to be 2405, and the distance, the arm is exactly 3.7 minus moment by the load. I just moved it here, this was not going to fit in. So moment by the load is the force. We just did it. I think we got this one because it's the same as it, which was 2405. And now the distance, the arm, we just, if this one is supposed to be 2/3, and this one was 1/3, so it's one third of this, and then you do your computation. Then if you did your computation very well again, you're going to get an arm of 123.33. That is going to be your arm from here to here. Remember, we're taking moments about here. This distance we use, and we use this distance. This one is for whole AB. This one is for like one third of AB. Then from here, you can just take that to the other side and solve for moment at A. And if I didn't make any mistake on my calculation, that should be minus 11856.65. Moment is in what? It's an arm, so arm will come with meters, and the force, Newton. These are units for the moment. So we have this now again. This negative tell that this moment is going to be anti-clockwise, because that's what we chose as our direction. So in terms of reactions, we have identified all the reactions. That means we have answered the question. The reaction at C, it was CY, which is answered. It was 247.27. We answered that. Number 2, what was reaction we had? We had another reaction at AX here, and that reaction was worked out to be negative 2405 newtons. And what reaction else we had? We had a momentum or circular reaction, which is 3, and it's going to be, what was it? It was moment. I just said momentum. Moment at A, of which I just computed here. It was negative 1185 6.67 Nm. So we just answered the question. These are the very important steps that you need to follow when you're doing your static equilibrium questions. You always have to start with those formulas. Summation of the forces along x is equals to 0. So summation of the forces along y is equals to 0. Moments around a certain point, their sum should be 0 again, so in a beam. So that's how it is. Thank you for watching. Please, if you spot any error in my math here, don't hesitate just to hit on the comment and tell me if I made any mistake. One of the viewers just told me that I did some mistake on my video, and I fixed it. Thank you very much, and hope you guys will spot if I also did any mistake here, but I hope I didn't. You guys trust me, right? So please subscribe, like if you find the video informative, to motivate me to do more. Thank you.